We will start with the first lecture of week 10, and in this lecture we will go through an example of a multi-pressure refrigeration cycle, which is somewhat different from the ones that you have gone through in earlier lectures. And let's first look at the problem statement, and then we will proceed with the solution of the problem. Okay, we have a two-stage compression system. We are given the pressure limits. That means 1.2 megapascal is the condensing pressure, and the 200 kilopascal is the evaporator pressure. Refrigerant is R134A, and we have a flash chamber which operates at 0.45 megapascals. Now if you read this next sentence after the 0.45 megapascal value, it tells us that part of the refrigerant evaporates during this flashing process, and this vapor is mixed with the refrigerant leaving the low pressure compressor. The mixture is then compressed to the condenser pressure by the high stage compressor. What we can infer from this statement is that in this particular system there is flash gas removal, but there is no intercooling, and that is something that we have to allow for in our solution and proceed with this particular arrangement. Then we are given the mass flow rate of the refrigerant through the low pressure compressor, which is also the mass flow rate through the evaporator, and we are told that the isentropic efficiency of the compressors is 80%. That means the compression process is not isentropic, but the actual process will be at a efficiency of 80%, and again this factors has to be also taken into account. And then we are asked to find out the mass flow rate of the refrigerant through the high pressure compressor, the rate of heat removal from the refrigerated space, and the COP of this refrigerator. The first thing that I will do is to show you a schematic of this arrangement. We are not given the schematic, so we can draw the schematic diagram ourselves, and that is the first thing that we will look at and see how the system works. After that we will move on to the solution by using the pH diagram of the cycle. If you look at this schematic diagram, you can see the condenser, and then we have the expansion valve, and we have a flash chamber at an intermediate state or intermediate pressure, and from the flash chamber the flash gas will separate out, which will be at state 3, and the liquid will then be throttled to the evaporator pressure from state 7 to state 8, and then it will absorb the heat from the refrigerated space, and it will be at state 1. From state 1 the low stage compressor will compress it to state 2, which will be now at the same pressure as the pressure of the flash chamber. So now the vapor coming from the flash chamber at state 3 and the compressed vapor coming from the low stage compressor, they can be mixed into this mixing chamber. So this what we have over here is actually, this is a mixing chamber, and we can identify that. And once the two streams, one at state 3 and state 2, are mixed together, the resultant state will be 3 prime, and of course the two mass flow rates will be added, the one coming from 3 and the one from 2, and then the total mass flow rate of the vapor will go into the high pressure compressor, it will be compressed to the condenser pressure at state 4, and then it will go through the condenser where it will reject heat, and that is shown over here. So that is the schematic representation of the system, and the next thing is to represent the same on the pH diagram. Now if you look at the pH diagram, the states points that we had shown on the schematic diagram are transformed over here onto the cycle. You have the vapor at state 4 entering the condenser. It is condensed to saturated liquid state, then it is throttled to the intermediate pressure of the flash tank, where the liquid is separated at state 7 and the gas or the vapor separates at state 3 over here. And then that liquid that we have separated in the flash tank is further throttled to the evaporator pressure and reaches state 8, then goes into the evaporator where heat is removed from the space. So we have this is the heat that is removed from the space, so this will be QL over here. So just QL, and then there will be heat rejection. We'll move to that in the condenser. So we have saturated vapor at the exit of the evaporator, which is compressed by the low stage compressor to state 2, and this process 1 to 2 is not isentropic because we are told that the compressor has a certain isentropic efficiency, and state 2 is then mixed with the vapor coming from the flash tank at state 3, and the intermediate or the resulting state is shown by this state point 3 prime, which will be at the same pressure but it will be at a different enthalpy and temperature. So you can see that state 3 prime will lie somewhere between states 2 and 3 but on the same constant pressure line, that is of 0.45 megapascals. This mixture, which is the mixture of states 3 and 2, will now be compressed by the high stage compressor to state 4, and again this is not an isentropic process but an actual process for which the isentropic efficiency is given. And then we will reject the heat from the condenser. That can also be indicated that we are rejecting heat, and that we can show by the symbols that we have been using, that is Q dot or QH. Bring it down over here. Okay. And as with similar problems, the problem can be solved in the usual manner. What we need to do is to find out the enthalpies at all the state points from the tables and by using the pH chart, or we can also refer to the superheated tables. So that is an option that we have. If the superheated tables are given, we can work out the properties at states 2 and 4 by using those, or we can simply use the pH chart and sketch the processes ourselves. Now let's start by looking at what we have given. We are given that the isentropic efficiency of each compressor is 80%, which I have shown over here. Then the mass flow rate through the evaporator is 0.15 kilograms per second. That is also given in the problem. Now we can start by finding out the enthalpies which are easily obtained from the tables. If you look at state 1, that is saturated vapor at 0.2 megapascals. So the enthalpy, specific enthalpy is given over here, that is obtained from the table. Similarly, H5 will be equal to HF, and that is the enthalpy of saturated liquid at 1.2 megapascals, that is also given. H6, because this is an isenthalpic process, is the same as H5. Now H7, again it is saturated liquid but at 0.45 megapascals pressure. We find that value from the table as well. And then H8 again is the same as H7 because it's another isenthalpic process. And H3 is Hg, that is saturated vapor at 0.45 megapascals. So these values initially have been obtained straight away from the table. Now look at how we will find out the enthalpy at state 2. If we look at this small representation over here, (1 to 2s) shows the process if it was isentropic, and because the actual process is not isentropic, it causes an increase in the enthalpy as compared to the enthalpy at state 2s. So 1 to 2 is the actual process line, and 1 to 2s is the process line if the process was isentropic. So what we can do, we can first work out the enthalpy assuming an isentropic compression from 1 to 2s, and during that process, because that process is isentropic, S2s will be the same as S1, which is equal to the saturated vapor enthalpy at 0.2 megapascals, and that S1 we can obtain from the table. The next thing that I have done is, by using the table, I've used the superheated property tables for refrigerant 134A, and we have to go to an intermediate pressure of 0.45. Now that pressure is not available in the superheated property tables, but we have pressures, one which is less than 0.45 and the other one which is greater than 0.45, which is 0.6 megapascals. So what we are assuming is that the entropy remains the same, that is 1.7334. So 1.7334 is the entropy that we want to be maintaining throughout from state 1 to 2s, and we find that corresponding to this value of the entropy, when the pressure is 0.4 megapascals, the enthalpy will be 406.83 kilojoules per kilogram, and corresponding to the same entropy, when the pressure is 0.6 megapascals, the enthalpy will be 415.34 kilojoule per kilogram. And that was the first interpolation, and now we will have to interpolate again by using the pressures. So we now know that if we keep the entropy constant at 1.7334 kilojoule per kilogram per Kelvin, at 0.4 megapascals the enthalpy is 406.83 kilojoule per kilogram, and at 0.6 megapascals the enthalpy is 415.34 kilojoule per kilogram. So we can easily interpolate to find out the enthalpy at 0.45 megapascals, which comes out to be 408.96 kilojoule per kilogram. Once we have got the enthalpy, this is the enthalpy H2s, and then we can use the definition of isentropic efficiency of compression, which is the work, ideal work, divided by the actual work, which in terms of enthalpy differences can be represented as H2s by H2s minus H1 divided by H2 minus H1. So this represents the specific work of compression if the process was isentropic, and H2 minus H1 represents the work of compression under actual conditions. So we have H2S is known to us, H1 we have already worked it out, so the only and the isentropic efficiency of compression is also given, so the only unknown is H2, which comes out to be 413.03 kilojoules per kilogram, and obviously we expect it to be higher than the enthalpy for the process if it were isentropic. So that is how we can find out the enthalpy at point 2. The next thing is to find out or locate state 3 prime on this line 2 3. So we on the pH diagram we have 3, we have 2, but we do not have state point 3 prime, and that is the next thing that we have to look at. To obtain state 3 prime, we perform an energy balance on the flash tank, and again I've shown that portion of the arrangement by this representation, and the control volume is shown by this broken line around the flash tank, and you can see that there are 3 streams which either are entering or leaving the control volume. So we have energy coming in at state 6, we have energy being leaving, we can see energy leaving at state 7, and again we have energy leaving at state 3. So the simple energy balance will be m dot 6 h6 is equal to m dot 7 h7 plus m dot 3 h3. But we know that m dot 7 is the same as m dot 8 is equal to m dot 1, because the same mass flow rate, that is the liquid refrigerant, goes into the evaporator and it reaches state 1 after passing through the evaporator, and this value is given to us, and that is also equal to m dot 2. M dot 6 on the other hand is the same as m dot 5 is and that is equal to m dot 4. That is, if we go back over here, you can see the mass flow rate that comes from the high stage compressor goes into the condenser. The same mass flow rate goes through the expansion valve from state 5 to 6 and then enters the flash chamber. So we again can come back to the solution, and now you can see that I've shown that over here, and that is equal to m dot 3 prime, because m dot 3 and m dot 2, when they combine together or they are added together, that is the total mass flow rate that is compressed by the high stage compressor. So m dot 3 prime is equal to m dot 3 plus m dot 2, and we substitute this value, that is, instead of m dot 6 we have m dot 3 plus m dot 2, and then we rearrange this expression. We take the m dot 3 terms, collect them on one side, so we have h3 minus h6, and then you will have m dot 2 h7. Over here we take it onto the other side, so it will be m dot 2 into h6 minus h7. Mass flow rate m dot 2 we already know, the enthalpies h3 h6 h7 etc. have to be, we can then find them out, because we know h3, we know h6, and then m dot 3 comes out to be 0.0525 kilograms per second. Remember, h3 is equal to hg at the intermediate pressure of, I think, 0.45 megapascal. Once we have got the mass flow rate, that is the total mass flow rate that is compressed by the this is the mass flow rate that is leaving the flash tank. So that is not the total mass flow rate, that is just the mass flow rate leaving the flash tank. the total mass flow rate will be the sum of m dot 3 and m dot 2 as we have identified earlier. Then we can perform another energy balance, and this time it will be the energy balance for the mixing process of the flash gas and the vapor from the low stage compressor. And for that again the energy balance equation is fairly straightforward, that we will have m dot 2 H2 plus m dot 3 H3, and that will be equal to m dot 3 prime H3 prime. And in this equation we know the mass flow rate, m dot 2 H2 is known, m dot 3 has been worked out, and H3 is also known. M dot 3 prime, as I just said, it will be the sum of m dot 3 and m dot 2, which is equal to 0.2025 kilograms per second, you can see, and that only leaves the enthalpy H3 prime, and that comes out to be 411.12 kilojoules per kilogram. Once we have found out the enthalpy H3 prime, then the point 3 prime can be located on the pH chart. So I'll go back to that pH diagram and just show you what I mean when I say it can be located on the pH chart. So what we will have is that we know that we have a enthalpy at state point 3 prime of around 411 kilojoule per kilogram. So at that particular value we can draw the straight line, and that straight line will then intersect this line 2 3 at a particular point, and that point will be point 3 prime. So this line which I have drawn over here corresponds to that value that we had just found out, that is 411.12 kilojoule per kilogram. So I can again show it over here, that this will be 411 approximately kilojoule and this is the value that will allow us to locate state point 3 prime on this line 2 3. Once we have located state point 3 prime, we can find out the entropy at state 3 prime, and then again repeat the process of compression from state 3 prime to state 4. So from the pH chart you can see that I have found out the value of the specific entropy at state point 3 prime, which is 1.74 kilojoule per kilogram Kelvin. And once we have got the solution, I will also show you how we can find out the value of the specific entropy by using tables. So that will be done once we have gone through the solution. I'll do that or show that to you later on. As we had for process of compression for the low stage compressor, similarly for the high stage compressor we have an actual process which is shown by the process line 3 prime to 4, whereas the isentropic compression would have been from state point 3 prime to 4s. And if we first consider the isentropic process, that is 3 prime to 4s, in that the entropy will remain unchanged, which will be equal to 1.74 kilojoule per kilogram Kelvin. And this time, because we already have a value of 1.2 megapascals in the superheated table, the interpolation is just a one-step process. That means we only have to find out the enthalpy at the given entropy. So we have the entropies in the table at of values 1.7226 and 1.7571, and the entropy that we have to work with is in between these two values. So we have these corresponding enthalpy values from the superheated property table, and then we find out the enthalpy of the refrigerant for a isentropic process for which the entropy value is 1.74 kilojoule per kilogram Kelvin, and that value comes out to be 432.22 kilojoule per kilogram. And so that is the enthalpy H4s. And once again we will use the value of the isentropic efficiency of compression. This time the ideal work of compression or isentropic work of compression was H4s minus H3 prime, and the actual work is H4 minus H3 prime. So we have all the enthalpies except H4, and that comes out to be 437.50 kilojoule per kilogram. And again we expect it to be higher than H4s, and that is shown by the value that we have worked out. So the mass flow rate, we were asked to find out the mass flow rate compressed by the high stage compressor, which is the same as m dot 3 prime, which is the sum of the two mass flow rates m dot 1 and, or we can say m dot 2 and m dot 3. So that is 0.2025 kilograms per second. In part B, we need to find out the rate of heat removal from the refrigerated space, and that is the heat removed by the evaporator. So across the evaporator, the enthalpy difference is H1 minus H8, and the mass flow rate that goes into the evaporator is m dot 1. Substitute the values, and the rate of heat removal comes out to be 26.355 kilowatts. And finally, the COP of the system, that is the rate at which heat is removed divided by the work of compression, and the work of compression will be the sum of the work of compression of the low stage and high stage compressors. Q dot we have already worked out. For the low stage compressor, the compression process is from state 1 to 2, so enthalpy difference is H2 minus H1, mass flow rate is m dot 1. Whereas for the high stage compressor, the mass flow rate we just worked out is m dot 4, and the enthalpy difference is from H4 minus H3 prime. Again substitute all the numerical values, and the COP comes out to be 3.14. Okay, now we can again go back to that point. That means how can we use the tables to find out the entropy at state 3 prime. Okay, and let's see how that can be done. Again, keep in mind that state 3 prime is at an intermediate pressure of 0.45 megapascal, and we do not have that value in the superheated property table, but we have values lower and higher than that. And again we can look at those pressures, that is 0.4 megapascal, and what we will try to do is to find out the entropy at 411.12 kilojoule per kilogram. Remember that 411.12 kilojoule per kilogram is the value of H3 that we had found out, H3 prime. So this 411.12 is H3 prime, and that was found out by using the energy balance. So corresponding to this enthalpy, if we are at 0.4 megapascals, the entropy will be 1.7483, and corresponding to the same enthalpy, if we are at 0.6 megapascals, the entropy will be 1.7189 kilojoule per kilogram Kelvin. And that is the first interpolation that we have to go through, and then we have to do another interpolation, and this time we will interpolate with respect to pressure, again keeping the enthalpy to be constant. That is, for an enthalpy of 411.12 kilojoule per kilogram, what is the entropy at 0.45 megapascal? And that comes out to be 1.7401 kilojoule per kilogram, and in this particular case it is more or less the same. That is the value which I had obtained from the pH chart. Slight differences can occur, that is expected, because in the pH, on the pH diagram you might have to draw the entropy lines yourself, but it is definitely quite a convenient way to obtain properties, and you can also visually see that you are following the correct cycle when you use the pH chart. And finally, let's also look at the same cycle drawn on a TS plot. Okay. You can see that over here this is not the exact cycle that we are working with, and I'll show you where this needs modification, but the basic arrangement is the same. You can see the state points 4, 5, 6, 7, 8, 1, 2 and 3 prime. State 5, so we have the isenthalpic expansion from 5 to 6, and that is the isenthalpic process line on the TS diagram. Similarly, we have the isenthalpic expansion again from state 7 to the evaporator pressure, that is at state 8, and this is again an isenthalpic process from 7 to 8. Then you have the heat rejection from 8 to 1. We have the flash gas separating at state 3, and we have the compression from state 1 to 2. Then the mixing of the two states 2 and 3 in the mixing chamber to give us the resultant state at 3 prime. And then again we have the compression from state 3 prime to state 4, and then we have the rejection of the heat in the condenser, and here you can see the portion which represents the sensible heat transfer from 4 to this point on the saturated vapor line, and then the latent heat transfer, the condensation process inside the dome. And the difference between this figure and the one that we have to actually draw for the problem that we solved is in the compression processes. We have identified that the compression processes are not isentropic, so they will have to be again modified by drawing a line, and I'll just try to show you that line over here. So the compression process is, when it is not isentropic, it will be somewhat different, and we can show it by a line like this. But it will, of course, we will continue with it where it intersects the constant pressure line. So the constant pressure line will be somewhere like this. So that is the actual process that you will have. You can probably delete this and just try to show it by a sort of a straight line, although it will be a curved line, but we can show it like this. So state point 2 will be like this. That means it will have an increased entropy and also an increased temperature corresponding to state point 2s. So this now becomes state point 2s over here, and this state point 2 will be over here. And similarly, we will have to replace this isentropic line by a line that is inclined to show the actual process line, and again that will be something like this, and again it will intersect the constant pressure line corresponding to the condenser pressure. and this time again the states will be states 4s, state 4s will be now over at this point, and then we will add state 4, which is the actual state, that will be over here. So this is now a representation of the same process, but this time on the TS diagram. So we will carry on with some more examples in the next lectures, and we will now move on to examples from the air conditioning portion of our course.